Hello everybody, I am Hari. Welcome to my class. So today we are going to learn something about monosaccharides. So let's start. Monosaccharides are the simple sugars and they are crystalline compounds and which are soluble in water. And most of the monosaccharides are sweet in taste. Okay, monosaccharides are simple sugars and are crystalline compounds which are easily soluble in water, and most of the monosaccharides are sweet in taste. So before we get into the topic, it's important to understand about the structures of monosaccharides. So we all know that monosaccharides or sugars are three-dimensional compounds that exist in our body, right? So it's difficult for us to draw them on the board or paper because they are just two-dimensional. So for us to understand them easily, Fischer has given certain formulas, certain projections. So those projectional formula are called when we are drawing the structures of monosaccharides, if we first understand how to draw them and how to draw them on the paper or on the board, then it will become easy for us to understand and to draw the structures of all the monosaccharide units. So in the Fischer projection formulae, the horizontal bonds, whatever the horizontal bonds were there, these horizontal bonds, they project out of the plane. So like this, for example, if this is the compound, they come forward like this. Okay, so they come forward like this, they come out of the plane. So we can imagine these four molecules, they come outside, and the remaining these two, they move backwards or into the board. Okay, so the vertical bonds away from the reader and the horizontal bonds, they come out of the plane towards the reader. Okay, so here we can imagine, or simply we can draw like this. Even this is the same thing. These two compounds, they are going inside into the board or into the plane, and the remaining molecules, they are coming out of the board. Okay, so this way Fischer projections are useful to understand about the three-dimensional structures of the monosaccharides and also to draw them on the paper or board. Okay, you see the structure, any of these structures in the paper, don't get confused. You may think like this is the carbohydrate molecule and this is not. It's not like that. All of them are same, but here the bondings that they have shown were different. That is just to make us understand how they are located, actual position of the molecules. Stereoisomerism, the main important character of the monosaccharide units is the stereoisomerism. What is stereoisomerism? Stereoisomers are the compounds that have the same structural formula but differ in their spatial configuration. Even though when two compounds have the same structural formula, the atoms that are located in the compound may get varied. So that is nothing but they differ in their spatial configuration. That is nothing but the spatial arrangement of the atoms in the molecule is nothing but the spatial configuration. A carbon is said to be asymmetric or chiral when it is attached to four different atoms. For example, this is the carbon which is attached to four different compounds like A, B, C, D. So all these atoms or molecules or the compounds are different, totally different from one another. So the carbon which is attached to four different atoms or groups, that carbon is said to be asymmetric carbon because all of them are not same. They are different. So that carbon is said to be asymmetric carbon atom or chiral carbon atom. So the number of the asymmetric carbon atoms in the given compound defines the stereoisomers. So there is a formula that is 2 power n. So here n indicates the number of chiral carbon atoms. Except dihydroxyacetone, all the remaining monosaccharides have at least one or more than one asymmetric centers. So for example, if we take the case of glyceraldehyde, it has, I'll draw the structure also, CHO, CH2OH, OH and H. Glyceraldehyde has one chiral carbon atom. So here n power 2 power n is equal to 2. So it is 2. So glyceraldehyde has 2 stereoisomers, which are also called enantiomers. So enantiomers are the stereoisomers that are mirror images of each other. So as we have discussed about D-glyceraldehyde has 2 isomers. Those 2 isomers are mirror images of each other. They are D forms or D isomers and L isomers. Let's discuss this with the example of glyceraldehyde. D-glyceraldehyde, L-glyceraldehyde. Okay, these two are mirror images of each other. For example, if we draw the line here, if we impose this structure here, we can see the same structure. This OH comes here, carbon comes here, hydrogen comes here, this one, this one. So if we impose this structure here, we get this structure. Again, if we impose this structure here, we get this one. So these two are mirror images of each other. So one is D-glyceraldehyde and another one is L-glyceraldehyde. So if we observe the difference between these two, here the hydroxyl group is attached towards the right side, and that is called D form. And if the hydroxyl group is attached to left side of the chiral carbon, this is called L form, L-glyceraldehyde. Left side L, opposite to left, right side D-glyceraldehyde. Okay, we consider glyceraldehyde as the reference carbohydrate to write down the structures of the remaining aldoses. Okay, it is because this contains a single chiral carbon atom, that is with 4 different atoms. All the remaining carbohydrates, all the remaining aldoses, they contain more than 3 carbon atoms. So we are taking this basic carbohydrate as the reference carbohydrate. The stereoisomers of monosaccharides can be differentiated based on the arrangement of groups or atoms at the carbon atom that is farthest from the functional group. For example, glucose has 6 carbon atoms. The functional group aldehyde, so it is an aldose. This is D-glyceraldehyde. So this is the reference carbohydrate. While we are writing the structures of the remaining carbohydrates, we take this as the reference. So the first one contains aldehyde group, the last one contains primary carbon, that is CH2OH. The carbon, the chiral carbon atom which is farthest from the aldehyde group, that contains the OH group on the right side. Then it becomes D-glucose. Okay, for example, if you have to write down the structure of L-glucose, L-glucose also the same structure, but it contains OH on the left side. So while we are writing about the structures of D forms, we have to take the D form of the glyceraldehyde, D-glyceraldehyde as the reference carbon, and while we are writing about the L sugars, we have to take L-glyceraldehyde as the reference carbohydrate. Glyceraldehyde is taken as the reference carbohydrate only for aldoses, not for ketosis. Okay. So this is the structure of L-glucose. So if we observe these two structures, we can see these two are mirror images of each other. See, OH is towards right side, left side. So these two are mirror images of each other. So these are the enantiomers. And coming to the number of isomers that are possible for the glucose, it is just by counting down the number of chiral carbon atoms. So if we observe this carbon, the first carbon, it cannot be chiral carbon atom because here the arrangement is like this. aldehyde. See double bond O. The second one. Here it contains aldehyde, OH, hydrogen, and the remaining whole thing as the R. So this is the chiral carbon atom. Coming to third one. Now this whole thing becomes R, hydrogen, OH, again R. Okay, R1, R2, because these two are different, not same. R1, R2, OH, H. So third carbon is also chiral, same. Fourth carbon, fifth carbon. Sixth cannot be chiral because it contains two hydrogens. So it cannot be chiral. So glucose atom, glucose molecule contains 4 chiral carbons. So 2 power n, 2 power 4, it is 16. So glucose has 16 stereoisomers. Out of those 16 forms, 8 are D forms and 8 are L forms. And mostly in the living organisms, the carbohydrates, the monosaccharides, they exist in D forms. Okay, and certain few other monosaccharides are there which exist in L forms. Example, L-arabinose, L isomers of certain sugars in the glycoconjugates also, they exist in L forms. Except those, all the remaining monosaccharide units in the living organisms, they predominate in D isomeric forms. So we have seen glycerolide contains 2 stereoisomers. Those are nothing but the enantiomers D glycerolide and L glycerolide, because it contains 3 carbon atoms. But aldoses with more than 3 carbon atoms, those are aldotetroses, aldopentoses and aldohexoses. These contain more than 1 asymmetric center. So since they contain multiple asymmetric carbon atoms, they can have more stereoisomers. Okay, so those are not the mirror images of each other. Diastereomers. For example, if you take the case of 4 carbon aldos, that is erythrose and triose. So these are aldotetroses because they contain 4 carbon atoms and aldehyde as the functional group. So if we observe the structure, they both have the same structural formula. So the structural formula for these two is the same. But if we observe the arrangement, are they mirror images? Let's find out. If we draw the line here, do they superimpose on one another? No. Here we can see the difference. At third carbon, here it has OH on the right side, but here it has H on the left side. So we cannot superimpose this form here. So these two are not mirror images. Then what? Because they have the same structural formula, they differ in their configuration, but they are not mirror images. So those isomers are called diastereomers or diastereoisomers. Okay, so you can observe even for the remaining aldoses, like these are the examples of aldotetroses. If we take the case of aldopentoses, example ribose, it has 2 isomers which are mirror images, D ribose and L ribose. Arabinose, D arabinose, L arabinose. Xylose, D form, L form. Lixose, D form, L form. Right? All of these will have the isomers. So for ribose, the D and L forms are enantiomers. Again here, these two are enantiomers. Means they both are mirror images of each other. D-xylose and L-xylose are mirror images of each other. So these two are enantiomers. Again, these two are enantiomers. But for D-ribose, the remaining forms will be diastereomers. Diastereomers. Here we have to understand this clearly, otherwise you may get confused. Why we are saying only for the D form, all these are diastereomers but not L. Diastereomers are not mirror images, right? Enantiomers are mirror images of each other. Right? Enantiomers of mirror images of each other. Diastereomers are not mirror images. Ribose has the structural formula that is C5H10O5. Even the arabinose has the same structural formula. Xylose, lixose, all these pentoses have the same structural formula, but they have difference in their arrangement. Right? So here if we take the D forms and L forms of each monosaccharide, they are mirror images of each other, so they become enantiomers. For this D form, except L form, because we have to exclude this because it is a mirror image. So we have to exclude this. For the remaining things, the D form of arabinose, L form of arabinose, D form of xylose, L, D, L, all these structures are diastereomers of D form of ribose. In the same way, the L form also, except this D ribose, all the remaining forms, all the remaining 6 structures will be the diastereomers because they get difference in their arrangement even though they have the same structural formula. Here we have to exclude its isomeric form, enantiomeric form, because those are not there. These two are mirror images, but the remaining things are not mirror images. Enantiomers are the mirror images. D and L forms are mirror images. So these two are enantiomers, these two are enantiomers, these two are enantiomers. But for any of these, for example, even for arabinose, for this D form, the remaining forms will be diastereomers, except its L form. For the L form of arabinose, except the D form, the remaining isomers will become diastereomers. So we can conclude one thing, that the stereoisomers are the structures with same structural formula but different their configuration. So here we have 2 types of isomers. One is enantiomers, other is diastereomers. Enantiomers are mirror images of each other. Diastereomers are not, that is non-mirror images of each other. So we can simply define diastereomers as the stereoisomers which are not enantiomers, or the stereoisomers which are not mirror images of each other are diastereomers. Both of them will have the same structural formula but difference in their configuration. But for enantiomers, they will be mirror images. Those are D form and L form. But for diastereomers, it is not about D and L forms. Except these forms, if the remaining things, remaining compounds, if they have the same structural formula but difference in their configuration, that is their arrangement, those will become nothing but the diastereomers. For example, we have D-glucose, which has the structural formula that is C6H12O6. All the remaining aldohexoses also will have the same structural formula, right? So let's know about what are the remaining aldohexoses. Next, D-glucose. We should not write L-glucose here because those two are diastereomers. So, those two are enantiomers. So we have to exclude the L form of this glucose. The next one, D-mannose. The last one I am writing here, D-tallose, L-tallose. Let's count down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 isomers. So while we have discussed about the stereoisomeric forms, we know that we can know the isomeric forms, number of isomers of a given compound by using this formula, right? So glucose contains 4 asymmetric centers, so just 2 power n, 2 power 4, so it is 16. So out of these 16, 14 are the diastereomers of glucose. Okay, what about the remaining 2? 14 are diastereomers. The remaining 2 are enantiomers. Simply we can write on glucose here. Okay, those 2 enantiomers are D-glucose and L-glucose. So if we take the case of D-glucose, for D-glucose all these 14 isomers are the diastereomers, or even if we take L-glucose, for L-glucose all these 14 become diastereomers and these 2 become enantiomers. Hope you all understood. Okay, enantiomers, diastereomers, both are stereoisomers, that is they have the same structural formula and difference in their configuration. But enantiomers are mirror images, diastereomers are non-mirror images. So if an isomeric form is not enantiomer, it must be a diastereomer. Okay, if it is an enantiomer, it cannot be its diastereomeric isomer. Okay, and the last one, that is epimers. Epimers are the 2 sugars that differ in their configuration at a single chiral carbon atom. So the 2 sugars that differ at a single chiral center, those are called epimers, D-glucose and D-mannose. Let's write them down. So if we look at these 2 structures, both of them will be same at all other carbons except the second carbon. At second carbon, this chiral center has OH on the right side and this chiral center has OH on the left side. Except this, the remaining structure is the same for both of these 2 sugars, right? So these 2 are C2 epimers because they differ at the second position, second chiral center. So those are C2 epimers. In the same way, we have another combination, that is D-glucose and D-galactose. These 2 are C4 epimers. So if you observe the structures of D-glucose and D-galactose, only they both differ at the 4th carbon, except that the remaining whole structure will be the same. So those 2 are C4 epimers. Hope you all understood. So if you have any questions to clear, please mention them in the comment section. Thank you.